Okay, so I had to give a break, and both time and location have changed, as you might have noticed. I'm recording directly on the tablet this time. So we were trying to obtain um, essentially a difference equation, um, and we were trying to find a relation between gk and yk by eliminating ck and ik in terms of the other two variables. Okay, so let me continue by writing our fundamental conservation law. This was the main equation that we had derived, if you remember. Uh, Now I want to leave gk and yk here, but I want to eliminate ck and ik. So I'm going to continue uh, by replacing those with their associated expressions. Okay, ck was expressed already in terms of y as a times y k minus 1, and the investment ik was, if you remember, equal to b times ck minus ck minus 1. So we have ck again here that I'm gonna still try to eliminate, plus gk. Okay, let's continue. We have a times y k minus 1. Now I will express the other ck's, so I will have b times ck will be again a times yk minus 1. But now I have ck minus 1. So because I have k minus 1 instead of k, so I will have to write this as a times y k minus 2. Okay, so I have k minus 1 and minus 1, which becomes k minus 2 plus g of k. Okay, so let's rearrange. So we can expand this, and I will have ay k minus 1 plus ba yk minus 1 minus ba yk minus 2 plus g of k. Okay, let's regroup. Uh, Basically, okay, let me also take these terms to the left hand side. So I have yk, okay, minus a plus ab times yk minus 1 plus ab yk minus 2, and that is equal to g of k. Okay, so you see, this is our output variable, and this is our input, in this case, input variable. And you see, in a very similar way that you have a differential equation of higher order, we have a difference equation of a higher order. Okay, now, so because we have k minus 2 means we have a second order difference equation. Okay, now let's so at this point, actually, we have a model for this system in the form of a difference equation, but I want to go further. Okay, I want to go further in the sense that let us define the system in state space. Okay, let us define the states. Okay, let's say that my first state, x1 of k, is CK, the consumption. Okay. Now, what is the interesting thing about this is that, remember, x1 of k is actually equal to a y k minus 1. So it's the one past value in time of our output variable. And let us also define the second state as directly our output variable, yk. Okay, so this is the gross national product. Okay, so you see you have yk as a state and yk minus 1 as a state with a constant factor. Okay, so now let's try to write the state equations in discrete time. What does that mean? Well, in discrete time, we have a structure like this: state space equations in discrete time are in the form. Basically, we have state at time k. This is the state vector, has to be equal to a times x at the previous state plus b times u at time k. Okay, this is our input, and x is the state vector. In this case, because we have two states, A is a 2 by 2 matrix, and because we have one input, B should be a 2 by 1 matrix. Similarly, the output is supposed to be, in this case, mind you, this is our output. So don't confuse it with the y of k. In fact, it's the same y of k, so that's not a problem. C times x of k, which is the state. All right, so let's try to write down the state equations. I will express x1 of k, hopefully in terms of xk minus 1. Okay, you see, each state has to be expressed as a function of the state at the previous time, and if the input is affecting that state, basically a term for the input. So x1 of k, we know that it is equal to c of k, and that is equal to a y k minus 1. And I know that yk is actually equal to the second state. Okay, so this one is equal to x2 at k minus 1. Okay, so I have x1 of k being equal to simply a times x2 of k minus 1. So that is one of our equations. In this state equation, there is no input term. Okay, let's call this 1. Now let's go to x2 of k. The second state equation is equal to, we know it is by definition y of k. And let us try to write this down. We know that it is a plus ab times y k minus 1 and minus ba or ab, doesn't matter, y k minus 2. Okay. Remember, we have, by definition, the first state was equal to a y k minus 1. So x1 of k was equal to a y k minus 1. A y k minus 1. Okay. So here I have a y k minus 2. So that becomes equal to x1 k minus 1. and I still have the b factor at the front. Okay, so let us write this down. This is a plus ab, again a plus ab. Now what is yk minus 1? It is equal to x2k minus 1, because y of k was equal to x2 of k. And this is the other term is minus b. Oh, by the way, did I forget? Yes, I forgot here the additional term. Let me correct that for you. So let's put this remember here. And I have basically forgotten here yk was equal to, yes, plus g of k, the input term over here. Okay, so that's going to be minus b x1 k minus 1 and plus g of k. So you see, I'm expressing x2 of k in terms of x2 at k minus 1 and x1 at k minus 1 and the input g of k. So that is the second equation that we have. So let's make this 2. Okay. So let me now put this into vector matrix notation. So hence we have I have the state vector x1k, x2k. That is equal to a 2 by 2 matrix times x1 k minus 1, x2 k minus 2, plus basically a column vector 2 by 1 times g of k. And let me fill in the terms in here. So if you look at this equation, x1 of k is equal to a times x2 of k. So you will have a 0 here and an a over here and no input term. So you will have a 0 over here. And in the second equation, if you look at it, you will have x2 of k being equal to minus b times x1, minus b times x1 k minus 1. And also you have a times 1 plus b times x2 k minus 1. Okay. And also we have an input term, 1 times g of k. Okay. So in terms of the state variables, let me also write down the output equation. The output equation is very simple, okay, because we know that y of k is equal to x2 of k. So therefore, y of k, which is a scalar, has to be a 1 by 2 matrix times the state vector, x1 of k, x2 of k. Okay, therefore, in order to obtain yk, which is equal to x2 of k, all you need to have here is a 0 and 1. Okay. Or in terms of the original variables, if you want to really write it down in terms of the original variables, you will have the same equations, right? You will have c of k, y of k, the two states, has to be equal to 0, a minus b, a 1 plus b times c k minus 1, y k minus 1, plus 0, 1 times g of k. Okay. And obviously yk is equal to yk. Okay, so there is no need for any output equations. All right. So let me give you an example. It is, fun. It is really fun to experiment with this. Experiment with a simulation of this model in MATLAB. I will give you one example. Okay, let's say what is the effect? Let's say somebody asks, what is the effect? What is the effect of government increasing spending by let's say a unity amount. Okay, so what happens is you are asking the question, what's happening if the state increases its expenditures by a unity amount? That means a unit step response. Okay, so let me show you a couple of curves. Let's say that the line represents state expenditures, state expense g of k, and also let's say that round samples indicate the consumption c of k, and let's also state that plus signs indicate gross national product, or y of k. Okay, so let me show you an example. Here's a graph. So this is years, okay, and these are our selected variables. Let's say that this is 1 and this is 2. Okay, I'll try to come up with a reasonable sketch. So here is our inputs. So we are saying that the state expenditures are undergoing a unit step increase. Okay, so this is our g of k. Okay, in fact, it's not continuous, right? But I'm indicating it as a line to be able to discriminate other variables. So what's happening here is that this is year 1, this is year 2, year 3, year 4, etc. Okay, so what's happening is that at year 0, nothing happens with the consumption. At year 2, year 1, nothing happens with the consumption. But at year 2, I believe it still remains at 0, but then it just starts rising. Okay, and then quickly kind of goes over, and so it just goes with a curve like this. Again, it is discrete, but I'm just indicating what kind of response curve we have. Okay, and more interestingly, if we take a look at what's happening with the gross national product, let me, I don't know, use maybe slightly different color. Okay, so what's happening with the GNP is that it just remains 0 for the 2 years, and then it just jumps to a higher value, and then it keeps rising, overshoots, and then gradually settles into this value. So it just goes on like this. Okay. So this is our GNP, which is YK. And this is our consumption, CK. Okay. So very interestingly, a unit increase, right? A unit increase in government spending results in twice the increase in uh, gross national product. Okay. Uh, So basically, it shows you that with increasing government spending, you can actually boost the country's output by uh, double the amount, which is kind of a prediction of this particular model. Obviously, you can argue whether this model is how accurate is this model, and it's the debate of economists, and there are probably better models than this, but this is how dynamic system modeling actually can be applied to a social or a socio-economic um, dynamic system model, okay, and actually to solve and you can, argue about how you can develop controllers for this kind of system, but it's still a very interesting example. Okay, so that's going to be all for this example, and I'll see you guys later.